Okay, hi everyone. Today we have a talk by Cassie Reeves. Cassie Reeves got her PhD in 2006 from the University of New Hampshire, where she did her dissertation work with Terry Forbes. Since 2006, she has been working as a research scientist in the Solar and Stellar X-ray group at the Harvard-Smithsonian Center for Astrophysics. She has been involved in the Hinode mission since launch, and she's currently the US project scientist for the X-ray telescope in Hinode. In addition, she is a recipient of 2006 prestigious Karen Harvey Prize for Early Career uh, Sciences. So please, Cassie, go ahead. You have 45 minutes for your talk and
Okay,
for discussion.
great. So I'm going to talk about the X-ray corona today. And this is not wholly my work. There's a lot of work by other people in here, so I wanted to say thanks to the Hinode and RESI and NuSTAR and SDO teams because I'm showing a lot of results from those missions. That is not my work. So, uh-oh. Oh, there we go. Okay. As most of you probably know, observing X-rays requires going to space. The atmosphere absorbs gamma rays and X-rays and ultraviolet light. This is a nice diagram from NASA that shows the Compton Gamma Ray Observatory. For those of you that remember that mission, in the gamma ray section, but X-rays and ultraviolet are blocked by the upper atmosphere. Visible light, radio waves can get through, which is why you can have things like VLA and EOVSA and observe those things from the ground. But if you want to see the sun in X-rays, you have to go to space. So here's a little summary of historical X-ray instrumentation. Much of this happened before I was a solar physicist. So I think there are people on the call that know much more about this than I do, but I'll just give you a little brief overview of the history of X-ray instrumentation. It started really with the space age, sounding rockets in the 50s and 60s. As far as I know, the first X-ray image of the sun was taken on a sounding rocket with a pinhole camera. And then the orbiting solar observatories were launched. There were 8 of them, and they had a mission to study the 11-year cycle of the sun. They were launched throughout the 60s and into the 70s. With Skylab, we were able to build much bigger, much more complicated telescopes because we didn't have the mass and the power restrictions that the OSO satellites had. And so there were several instruments on the Skylab Apollo telescope mount. This is an image from SO54 X-ray telescope, which was built by American Science and Engineering in Cambridge, which is one of the predecessor organizations to the CFA. So we've been doing this for a long time. Next came the Solar Maximum mission in the 80s. It had the dubious honor of being the first unmanned thing to be repaired by the space shuttle because it broke shortly after launch in 1980. And it had several instruments to study the sun, including a coronagraph, but it had a hard X-ray spectrometer and a softer X-ray spectrometer. The Normal Incidence X-ray Telescope, NIXT, was a rocket launched by Leon Golub in 1991. And then most people are probably familiar with YOCO, which was also called Solar A before launch, which had a hard X-ray telescope and a soft X-ray telescope and a Bragg crystal spectrometer on it. So we've been looking at the sun and X-rays for quite a long time. Recent X-ray instrumentation, I I've sort of organized it in terms of spectrometers on the left and imagers on the right. The spectrometers, everybody's probably familiar with GOES. There was also a Minsk CubeSat. Cronus Photon was a Russian mission launched late 2000s, I think. New Star is an astronomical mission, but they also look at the sun sometimes. So the things in the middle column are things that do imaging and spectroscopy. The Foxy rockets, there's been a series of rockets from Foxy that do imaging and spectroscopy in the hard X-rays. And of course, RESI was a very successful mission that did hard X-ray imaging spectroscopy as well. And then for the imagers, we have Hinode XRT, and I'm being very generous with my definition of X-rays here. And I'm also including the SDO AIA hotter channels, the 131 and the 94 angstrom channels, which image hot plasma between, say, 8 and 10 million degrees. I've probably skipped some things, so please don't be offended if I didn't include your favorite instrument here. I'm just trying to give a general overview of the kinds of instruments that we have available to us or have had recently available to us um, in our observations. So I'm going to talk about a few open questions having to do with the X-ray corona. The first is, how is the released energy partitioned and distributed in solar eruptions? Another open question is the corona heated by nanoflares? And then also, what are the sources and the composition of the solar wind? So starting with the first question, how is released energy partitioned and distributed in solar eruptions? One interesting aspect of solar eruptions is that we see a continual CME heating. These are some observations from Jinyi Li, although she's not the only person who's noticed this. But she estimated the conductive cooling time and found that it's much smaller than the lifetime of the event. So that indicates that you have some continual heating happening during the CME. Nick Murphy wrote this really nice paper in 2011 talking about some of the possible mechanisms for this continual heating. Could be reconnection outflow from the current sheet, kink instability, small scale reconnections, wave heating, energetic particles, ohmic heating from a flux rope current. So if you're interested in exploring those more deeply, I encourage you to read that paper. Hot flux ropes, it turns out, are very common in the corona. We've started to learn this through AIA observations, where we have continual observations of the sun, and so we can get good statistics on hot flux ropes and how often they exist. This paper by Nindos in 2015 showed that something like half of the eruptions have a hot flux rope associated with it. And if you look at XRT observations, here's an example of an XRT observation where the hot flux rope was visible in the XRT, but not so much in the AIA hot 131 channel. So that indicates that this 50% is perhaps a lower limit and that maybe there are more hot flux ropes than that even. There have also been observations of current sheets or current sheet-like structures in the corona. This is on the left is an observation by Sabrina Savage, where she's observed an eruption that shows a hot component erupting out, and then a long linear plasma sheet structure that is probably associated with the current sheet, and she sees a lot of flows in that region. Luckily for us, the ice slit was right along this current sheet. So ice is a spectrometer on Hinode. And so Enrico Landi was able to look at the thermodynamics of the current sheet region and the eruption. This top portion shows the CME itself. It's got a cool and a dense component seen in the helium-2, and then a warmer and less dense component seen in the iron-7, I guess that is. And then in the hotter channels, they saw a current sheet, which they saw in spectral lines up to iron-16, which is relatively hot. So one thought about how these flux ropes are heated is that they may be heated by accelerated particles. This is one example that was observed by Lindsay Gleasoner and Hazel Bain, wrote separate papers about it. This is a really nice eruption at the limb that you can see the flux rope in the AIA-131 and the AIA-94, which show hot plasma in AIA. And they found a ReSi source in this erupting flux rope. The ReSi source is about 18 to 40 kiloelectron volts, so it's a fairly hard source. There are probably non-thermal electrons in that source. And if you look at the derivative of the 131 angstrom light curve in that flux rope, it mirrors the light curve for the 18 to 40 kiloelectron volt source. And that's an indication, that's kind of a Newport effect like phenomenon. So that indicates that perhaps those accelerated electrons are losing their energy in the flux rope, and that's contributing to heating. This is another really nice observation of a flare at the limb, showing the 131 angstroms in the background and then some ReSi sources on top of it. We get a nice double ReSi source. So we're seeing the loop top source and then above the loop top source. And this shows that there's heating in the outflow regions. So this heating may be due to shocks or maybe turbulence due to the reconnection. This is a nice recent paper by Ben Chen that has been submitted, so I hope he doesn't mind me showing this. But this is UEFSA data overlaid on the AIA-131 on the left, and the Hinode XRT in the middle, and the emission measure from the 9 to 11 million degree plasma on the right. And this shows that there is non-thermal emission from the plasma sheet, central plasma sheet, where you would expect the current sheet to be, but also at the legs of a potential flux rope going up and around and through the loop at the top there. So this is kind of a combination of those previous two observations where you have non-thermal particles in the outflow region, and so maybe there's some heating there, and then there's also particles at the foot points of a potential flux rope, which could also be contributing to the heating. And this is another observation. This is a different orientation. So now the flare loops are oriented perpendicular to those other events. We see a lot of super Arcade downflows, which are these dark downflows that are flowing down through the hot plasma sheet late in the eruption. And what we find is that in regions where there's a lot of turbulence or a lot of these downflows, there tends to be more heating than places where there are fewer of these downflows. And also that the downflows tend to correspond with viscous and adiabatic heating. So the next question I'm going to look at is the corona heated by nanoflares? And this is a long-standing question. And one way to get at this question is to try to understand if flare-like phenomenon scale all the way down from the big flares that we see all the way down to much smaller events that we don't see. So we know that small flares exist below the GOES and the RESI sensitivity. We know that thanks to sensitive spectrometers such as NuSTAR and the Russian Sphinx, or the Sphinx was on the Russian mission. I think it was a Polish instrument. And so these are some results by Lindsay Gleasoner and Alec Engel, where they looked at the distributions of emission measure and temperature in very, very small events. So the question is, could lots of these very small events heat the corona? And what's necessary is a broad distribution of hot plasma. That's what you would expect if you were having nanoflares, is you would have a broad distribution of hot plasma, and that would contribute to the coronal heating. So in the image by Gleasoner et al., the red are microflares viewed by RESI, the blue come from the GOES, and then the NuSTAR flares, microflares that she saw were even lower energy than those.
But what is the numbers 10, 100, and 1,000 in this plot?
That's a good question. I don't know the answer to that. I would have to go back and look at her paper. I think they are related to the energies, possibly the GOES class, because I know I have a plot later with similar lines on them that indicate the energies in the flares. The Sphinx plot from Alec Engel has two small flares on it. The purple and the blue are from GOES, and then they christened their lower class flares Q and S for reasons I don't remember. So an S flare is, I believe, 10 orders of magnitude lower, and a Q flare is 100 orders of magnitude lower than a, or 10 times and 100 times lower than an A class flare. So these smaller events certainly exist, and with these sensitive spectrometers, we can start to see them. So one thing people decided to try to look for with XRT was a faint, hot, active region emission. So this would be something that you would expect to see if there is a nanoflare contribution, you would expect to see faint, hot emission from active regions. And so,
Kathy, I have one more technical question.
sure.
You already shown a few plots from XRT, various filters. Could you briefly just overview like the meaning behind different filters?
Sure. So XRT has several analysis filters, and they range from thinner to thicker. And XRT has a very broad temperature response. So the thinner filters can see emission from kind of 1 to 200 angstroms, which is maybe on the order of, 2 million degrees or more. The titanium poly, which is what this image is showing, is kind of a medium filter. It's not the thinnest. The two thinnest are the aluminum poly and the aluminum mesh. The Ti-poly is next, so it's sort of the third thinnest, I guess. And then anything that's got beryllium in it is a fairly thick filter. So that tends to restrict the XRT response to hotter emission.
And what are the main contributors? Is it free or ionized iron emission?
It's largely iron emission, but because it's sort of iron 17, not iron 17, 17 angstroms. Iron, maybe it is iron 17. Helen will correct me. Anyway, yeah, there's a broad range of lines that are seen by XRT. Also, the free is also seen, but there's a broad range of lines. Anything that emits between 1 to 200 angstroms for the thinner filters can be seen by XRT. So it's not like AIA, where AIA has a thin, a narrower temperature response that's centered around an iron line. XRT has got a very broad temperature response that picks up a variety of lines from the spectrum. And there's a fairly nice paper by Brendan O'Dwyer, I think, that catalogs exactly which lines are in each filter based on what's happening. Is it a flare? Is it an active region?
Okay, great. Thank you. Yeah.
So for XRT, this paper by Joan Schmelz used XRT and RESI to try to constrain this faint hot component. And they found that maybe that there's a faint hot component here. The Sphinx spectrometer, people have also done work with that to try to get a handle on whether or not there's this faint hot component. They with this spectrometer, they averaged over a month, and they got evidence for a hot component with 3 orders of magnitude less emission measure than the warm component. Unfortunately, Sphinx wasn't up for very long. I think it was only up for maybe about 9 months. But people have looked for evidence for the hot active region emission with AIA and ICE. And its top image is from a paper by Paola Testa and Fabio Reale, where they looked at AIA images and compared them with the ICE emission, and they found that they are able to image the hot plasma using the 94 channel and the 131 channel, the 94 and the 335, sorry. So the 94 angstrom channel shows the hot plasma that's very similar to the emission in the calcium 17 line in ICE. And Harry Warren did a nice study of active region DEMs with ICE, found that they're strongly peaked at 4 million degrees for strong magnetic fields, but they're a little bit more broad for weaker magnetic fields. So the strongly peaked means that there's less room for the nanoflare theory to be true, because you need this broad distribution. But so people have started to look for constraints from the hard X-ray instruments, because they can give you stronger constraints on the hotter end of the spectrum. So on the left is an image from the Foxy 1 rocket, and they found no real evidence for a hot component higher than about 1 million degrees or 10 million degrees. And on the right is a observation from NuSTAR from Ian Hanna, and they also put some limits on the high temperature component in the quiescent ARs. In both of these observations, there was not any evidence from Foxy or NuSTAR for non-thermal particles, but these were each only one active region. So there's certainly more work to be done here.
Kathy, this is Angelus.
Hi, Angelus.
How are you doing? Here in this particular slide, can you kind of show with your cursor what sort of distribution you would be expecting if that hot component was present, and what sort of maximum temperature people are thinking about?
Yeah, I think opinions vary a little bit, but you would expect to have sort of a more broad distribution down in this range. The idea is that if these nanoflares are happening and they're happening all the time, you should be getting a variety of temperatures over the lifetime of uh, the loop. So each loop is getting activated and then fading. You should have a broad distribution of temperature. So you should see some more emission down here. Is
Is
my
there a
kind of
limit to that temperature, how hot that component can get?
sort of 8 to 10 million degrees, or maybe 6 to 10 million degrees. And some studies talk about not really a temperature, but more a slope of this DEM.
I see.
If this slope is uh,
Softer.
yeah, softer, exactly, then that would be a better indication of nanoflares.
Thank you.
So a lot of the questions about um, coronal heating and nanoflares have really focused on active regions. So I wanted to give a shout out to this Quiet Sun study because I think this is a really interesting way to go. This is from Kuhar et al., and they looked at quiet sun regions with NuSTAR, and they are starting to catalog the energy content of these events. So on the left is a image of this little event. The 335 angstroms from AIA is in the background, and then there's a um, contours showing the NuSTAR emission on top of that. And on the right shows a similar kind of plot um, with the EM emission measure as a function of temperature, showing where these, they call them quiet sun flares, um, where these events are lying down. And the active region microflares that were discovered by NuSTAR are up here, so that gives you some context with those previous graphs. The quiet sun flares are here, and then the lines are showing um, the essentially what the flux would be in GOES. So this would be a tenth of an A-class flare, and this line would be a hundredth of an A-class flare. So I think those lines in the previous plot were showing something similar. So they only have a few of these so far, but there are quiet sun studies underway with NuSTAR to get more statistics on these kinds of events. And that will really be an interesting study to try to understand the contribution of these very small events um, to the heating in the quiet sun. So the final question I wanted to talk about was the sources and composition of the solar wind. This will be a really salient topic, I think, coming up because of the launch of Solar Orbiter and the launch of Parker Solar Probe. We're going to start to get some really interesting synergies between the the remote sensing instruments such as XRT and AIA, and the in situ instruments on Parker Solar Probe and Solar Orbiter. So one big result from XRT was outflows, or Hinode in general was outflows near active regions, and the idea is that these outflows might be contributing to the slow solar wind. So on the right, I'm showing an image from XRT, which shows the outflows, and then on the right is a raster scan from ICE, which shows the red shifts and the blue shifts, and it shows of the same active region, and it shows that those are definitely outflows there. So that's one possible source for the slow solar wind. And David Brooks did a really nice study of the abundances of these outflows. On the right is a ice scan of the whole sun, actually, with a model of the magnetic field superimposed on that. So reds are outflows and blues are inflows. And in this map, the green lines are the open field lines, and so they tend to overlie the red regions. Oh, I think I have that backwards. I'm sorry. The reds are the inflows and the blues are the outflows. I should know better. Anyway, the open field lines tend to overlie these regions where you have outflows, and then the abundances are enhanced 3 to 4 times over the photospheric abundances, which matches up nicely with the solar wind. The solar wind has more coronal abundances, as I understand it, than photospheric. So this matches up with the idea that these outflows may be a source of the slow solar wind. There's also a study done with XRT that showed that there were bright points, lots of brightenings, abundant brightenings at coronal hole boundaries. So in this image, the background image is an XRT AL poly image, and the black line is the coronal hole boundary, and then the little green dots are all the places where they saw brightenings over the course of some time period. And they find that these coronal hole boundaries are abundant with brightenings, indicating there might be frequent reconnections there. And this study suggested that these brightenings at the boundaries might also be a source of the slow solar wind. This kind of brings us to the idea of X-ray jets. This is a nice movie from Jonathan Certon's paper in 2007. And this just shows how frequently these jet events happen in the polar coronal hole. And they tend to happen kind of all the time. The statistics down there from a paper by Antonia Savcheva. So you get 60 to 100 jets per day, mean velocity of 160 kilometers per second. You do see velocities up to 1,000 kilometers per second. So they're happening all the time. And they have been traced into the solar wind. This is a study by Yu et al. From 2014, where they looked at 3 jets from XRT, and they traced them into the solar wind using, I think I'm not sure if it's LASCO or stereo, but the coronagraph, and it's both LASCO and stereo, and then SME, which is a imager that images eruptions as well. So there is some evidence that these jets can have an effect on the solar wind. This study found that it was something like 3% of the mass of the solar wind, so it's not a huge amount of the mass, but they may have a real effect on the structure of the solar wind. This is a study from Ulysses, done by Marcia Neugebauer. And the top plot there shows the latitude of Ulysses as a function of time, and then also the distance. And what she found was that there are these velocity fluctuations up and down, and she called these microstreams, and found that the proton temperature and the normalized flux are greater in the peaks, and they were consistent with the density and temperature and high speeds of X-ray jets. So that's kind of an interesting possible connection there. people have looked at the composition of jets. This study by Lee et al. Found that they were the abundances in jets were close to photospheric, which is kind of what you'd expect in the fast solar wind. And a few studies have been done looking for evidence for chromospheric evaporation in jets, which is what you would expect if there are photospheric abundances. So in these two studies, increasing velocity with temperature is an indication of chromospheric evaporation, which would imply photospheric abundances, although the abundances were not measured directly in these studies. But interestingly, not all jets show this relationship. So Samaya Farid has just submitted a paper to APJ, where she does a study of several of these jets and find that some of them show this relationship where you get an increasing temperature as a function of velocity of the plasma and the jet spire. But some of them don't show this relationship. So that's kind of an interesting twist. And given that we're talking about jets, I just wanted to mention these interesting recent Parker Solar Probe results. This is from the Bale et al. Nature paper, where they see these alphanic fluctuations in the heliospheric magnetic field. And one, they've called these switchbacks. And one thought is that these might be the remnants of coronal jets. So I stuck a nice cartoon down there. It gives you an idea of how that might happen. You have some sort of interchange reconnection, jet reconnection at the corona, and then that disturbance propagates out and is seen out at 35 solar radii by Parker Solar Probe. So I expect that there will be a lot of really interesting work to come out from combinations between Parker Solar Probe and Solar Orbiter and the remote sensing instruments on this topic. And one final thing I wanted to mention about jets that I think is also pretty interesting and also pretty related to Parker Solar Probe and Solar Orbiter is that hard X-rays have been seen in jets. This image is from a paper by Lindsay Gleasoner. Sophie Musset has also done a really nice statistical study of these that just came out this year. And what Lindsay finds is that there's an elongated source in this active region jet, and it corresponds with a type 3 burst in radio, indicating that there's open field for the accelerated electrons to travel along. So that's another open avenue of investigation, I think, for the combination of remote sensing and Parker Solar Probe. So I wanted to give a shout out to some future X-ray instruments that are coming online soon. There's the Spectrometer Telescope for Imaging X-rays, or STIX, which is on Solar Orbiter. So that launched on February 9th, and it turned on April 14th, and I think everything is going great as far as I know. So we should be seeing data from that real soon. And then we have a rocket flight coming up in, well, it was supposed to launch in May, but it didn't because of the COVID-19 pandemic, unfortunately. So the launch has been delayed probably until 2021. But this is a spectrometer that will look at the X-ray spectrum kind of between maybe 3 and 20 angstroms. And it's a region of the sun that we haven't really looked at with an imaging spectrometer since maybe the SMM days. So, so that'll be really nice. And then finally, I wanted to give a shout out to FIRSE, which is our MIDEX that we've submitted to NASA. FIRSE stands for the Fundamentals of Impulsive Energy Release in the Corona Explorer. And our science questions overall, we're going to deduce how solar energy is suddenly released and transformed. And our questions are, what are the physical origins of space weather? How are particles accelerated, and how does energy transport happen at the sun? How is the solar corona heated? So this mission is really very well situated to address some of these questions that I mentioned in the talk today. It has 3 instruments. It's got a version of the FOXY instrument that's been flown on the rockets before. Has an instrument called THADIS, which is thermal and dynamic imager for the sun, which is a narrowband EUV imager. High spatial resolution in the 131 and 284 angstroms, and spectrometer for temperature and composition, or STC, which is an X-ray spectrometer similar to the one that was flown on the Minx CubeSat. So FIRST will launch in 2025, near the peak of solar activity. So I think that's all I have to say. I was pretty good on time. I didn't have a clock, so I wasn't sure how I was going to do, but
Okay,
there's some time for questions.
Yeah. There are many people, so please try to speak one by one. If you have question or comment, we are open for that. I see a few unmuted microphone. Hugh? Hugh, muted. I do not see any unmuted microphone at this point.
I have a question.
Angelos, yeah, go ahead.
I have several, but I can.
Yeah, go ahead.
One question related to the hard X-rays from the jets. What do you expect to get from more hard X-ray measurements to those in particular?
Angelos, could you speak closer to your microphone? I barely hear you.
Okay. So what I'm saying is, what do you expect to get from the hard X-ray measurements of those jets? What sort of physical parameters you hoping to get?
I mean, I think one thing that's pretty interesting is more events that are similar to this one, where we could maybe hope to trace the effects of the jets out into the solar wind. And we could also get better parameters on whether or not there are non-thermal particles in most jets, or if it's only a handful. With FOXY, we'll have the FOXY instrument on FIRST will have better sensitivity, so we'll be able to understand how prevalent the non-thermal particles are in the jets.
But you don't really have access to the heavies, right? So we don't know if there's any heavy ion acceleration.
I think that's right, yeah.
Yeah.
More questions? Yeah, go ahead. Yeah.
My other question has to do with, of course, the hot flash ropes, which is a pretty hot item. Well, they come in, as you implied, they can be multi-temperature. So in order to capture or to know how many, whether they exist in every eruption, which I think they do, we need more, I guess, thermal coverage, right?
Yeah.
Yeah.
Yeah, I think, an ideal situation would be sort of an AIA-like field of view and cadence, but with kind of an XRT filter, because XRT, since XRT has this broadband temperature response, it's better, like in this case that's shown on the slide, it can pick up the temperature, the hot temperature is a little bit easier because it's not limited, by the narrow band emission. So that would be one way to
Broadband.
yeah.
Yeah, that's true. Thank you.
Okay. Hugh is unmuted. Hugh, do you have questions? Go ahead.
Yeah, am I unmuted?
Yeah.
Okay, so I think I wanted to make the case that the case for nanoflares is kind of overstated. If you look at your nice image, the Kuhar et al. Image from NuSTAR, you see a couple of quiet sun events, and they're very faint, but they're also extremely localized and they're extremely brief in time, right? But in the background of those quiet sun events, you see the corona, which is diffuse and steady and hot, and it obviously is not being heated by events like this. It's kind of a non-question. So I think that there's really no convincing evidence that the nanoflare idea really works.
I mean, I think you have a real point there, because a lot of the nanoflare heating studies have been done on active regions, and that's where a lot of the work has been focused. But we know the quiet sun is hot too, so something else is going on there, or something is going on.
Right.
Whether it's nanoflares or not, I don't know, but yeah, that's a good point.
Yeah, Hugh, further to this, the initial observations from probe, they seem to suggest that even small jet-like or surges are able to accelerate heavy ions, even though you would not expect that to be the case. So it is something interesting going on for those small eruptions. I don't know if it bears to the coronal heating, but it does bear to acceleration questions, I think.
Interesting.
It's very unusual.
Can I ask a question?
Mhm.
For the solar probe measurements, and it was pointed out that there might be the remnants of the jet. In that cartoon, as you show, that king is produced close to the sun. How can that king still not straighten when it propagate to 30 solar radii?
Yeah, that's a good question. You look at this cartoon and you sort of think, well, that's just going to straighten right out. I know people have done some simulations where they have tried to replicate this, but I think it's a really open, active area of research right now. Obviously, the picture is probably not as simple as this cartoon. So yeah, that's a good question, and it's something that is needs to be looked at in more detail, I think.
Good. Other questions or comments?
This is Ben.
Ben, go ahead.
Yeah, I have one quick question. So for the quiescent active region outflows, you have mentioned spectroscopy methods. Have anybody reported those outflows in, say, AIA images when those outflows are viewed at LIM, for example?
I don't know, actually. I can't think of any studies off the top of my head, but that doesn't mean they don't exist.
Yeah, Angela has a comment.
We did the work with stereo with Guillermo Sternbrook, looking at process images in 171 and 195, and we see some sort of quasi-periodic outflows all around the sun, about 80 kilometers per second or so. But of course, you cannot trace them for more than I don't know, 100 megameters, something like that. Very, very. I mean, we lose signal. So in order to resolve this issue, we kind of need very sensitive off-limb, say, UV observations to be able to see really make it anywhere to the close to open lines.
Is this ongoing work, or do you have a published paper so we can look into?
I don't know, 10 years ago, but and there are some works also with Hinode on looking sort of like speaker-like structures all around, trying to measure the outflow. It's very difficult to measure, right? You need statistical techniques because you cannot resolve individually, except for jets. But jets, we know they make it out. I mean, we know this since Soho, the Soho times. But yeah, this is basically an issue with signal-to-noise ratio, and there's, of course, the limited field of view of AIA, which is too small to reach the open field, say, about 1.2.
Okay, great. Thanks for letting me know. I'll send you an email, ask for the link. Thanks.
And I also want to ask Kathy to send us an excellent review here, because there's a lot of material. Very comprehensive.
Good. Other questions or comments? I'm trying to look through microphones. All microphones are muted. While maybe other comments or questions arise, I want to make a brief announcement about the format of this event, about this webinar. This webinar will change its format as of next month, as of May. It will be integral. It will become an integral part of a new Drive Center solar flare energy release, and the webinar will change time and date. It will happen each third Friday of each month at 1 p.m. Eastern time. And I will make an announcement about that in the Solar News. I just want usual participants, like most frequent participants, to keep in mind that the time and date will change, and the next event will happen on May 15 with Lindsay Glessner, presenter, but the web address will remain the same, so you can check schedule the webinar at the same links, as same web page. And again, keep an eye on Solar News announcement. Will happen in a couple of days. Yeah, so let me look at the microphones. All microphones are muted, I think. If I overlooked anyone, please go ahead and ask. Leon, go ahead. Yeah.
I have a comment regarding these jets. Now, it seems to me that there is also a change. If you look at Bale's paper, there is a change in the magnitude of the magnetic field, in the absolute value. So this could be also CIRs. I don't see why not, where you have co-rotating interacting regions, because you are far from the photosphere, from the corona, and there you have already a spiral. So as you have slow wind and fast wind coming from these equatorial holes, they can cause some of these what they interpreted as jets, I believe.
I think they're on a time scale that, I think the fluctuations are on a time scale that's too fast for that. I'm definitely not an expert on these, but that was kind of my impression from sitting through a bunch of talks on these at the AGU, was that the fluctuations were happening a little bit more rapidly than you would expect from something like that. But you know, that's definitely something you should like go hunt down Justin Casper or Stuart Bale or something, or somebody and ask, or maybe Angela has an opinion. I don't know.
Okay, thank you.
Angels, you have more question or comment?
I'm okay. No, good.
Fine. Yeah, I'm looking through microphones. Every microphone is muted, so I think that we can close the session. So thank you very much Casey, so everything will be available online, recording and presentation. So please visit the page and come again. Thank you. Bye.
Thank you.
Thank you very much, Kathy. Talk.
Bye, everyone.